Let us do one corollary. So, suppose x1, x2, xn is a random sample from normal mu sigma square distribution, where mu is anything from minus infinity to infinity and sigma is positive. So, let x bar be the sample mean 1 upon n summation I is equal to 1 to n xi, and suppose s square is 1 upon n minus 1 summation I is equal to 1 to n xi minus x bar, to which we call as a sample variance. Then root n x bar minus mu by sigma goes to normal 0 1, and root n x bar minus mu by s goes to T n minus 1. The proof is very simple, because x bar is a linear combination of independent normals, so it has to be normal. If it is normal, then I know the parameters are its mean. So, expected value of x bar is always mu, so mean is mu, and its second parameter is the variance of the variable, which is variance of x bar, which is variance of 1 by n summation I is equal to 1 to n xi, which we know is nothing but sigma square by n. In fact, I gave this one as one of the exercises. So, x bar is normal mu sigma square by n, and we have also done a result which says if x1, x2, xn are IID normal mu sigma square, then n minus 1 s square by sigma square is chi square or n minus 1. We also know that from the result which was done in the last module that they are independent. So, what you have is I standardize this x bar. So, root n x bar minus mu by sigma is normal 0 1, n minus 1 s square by sigma square is chi square or n minus 1, and the two are independent. So, this is which is normal 0 1, this is chi square on n minus 1 divided by n minus 1. So, this would have T n minus 1, because these two are given to be independent. So, this is nothing but root n x bar minus mu by s is T n minus 1. So, one knows how one can get the T distribution with n minus 1 degrees of freedom from a normal distribution, which is root n x bar minus mu by s, where x bar is a sample mean based on IID random variables from normal mu sigma square, s is the corresponding sample variance. Let us do another example. So, suppose you have a sample x1, x2, xm from normal mu 1 sigma 1 square. You have another sample y1, y2, yn from normal mu 2 sigma square. Further, suppose that the two samples are independent. So, I have taken two samples, one of size m, one of size n, and suppose I take these samples independently, and both these samples are random samples. Define s1 square as the sample variance based on the first sample, s2 square as the sample variance based on the second random sample. Here x bar is the sample mean based on the first sample, y bar is the sample mean based on the second. Then if I look at the ratio of sample variances with proper normalization, it turns out to be a f distribution with m minus 1 degrees of freedom and n minus 1 degrees of freedom. So, what it suggests is that f distribution one can get through the ratio of variances. Of course, one has to divide the corresponding population variances to get the f distribution. So, if one is sampling from normal distribution and one is getting two samples, this is how one can get the f distribution. Let us try to see how do we do it. Now, we clearly first sample is based on m, so m minus 1 s1 square by sigma 1 square is chi square on m minus 1. Second is sample is based on n, so n minus 1 s2 square is the sample variance for the second, so n minus 1 s2 square by sigma 2 square is chi square on n minus 1. Also, since this is based on x, this is based on y, and the two samples are independent, so that means these two quantities would be independent. So, I have got two chi-square distributions which are independent. So, that means if I divide it by their degrees of freedom, so which would be s1 square by sigma square only, I divide this by its degrees of freedom, which would be s2 square upon sigma 2 square. They are given to be independent. So, this would have f on m minus 1 and n minus 1 degrees of freedom. So, which is equivalent to saying that sigma 2 square s1 square divided by sigma 1 square s2 square is nothing but f on m minus 1 and n minus 1 degrees of freedom. Let us do the following remark. Suppose x is Tm, that means it has a T distribution with m degrees of freedom. Then I know that x can be written as z upon square root of y by m, where z is normal 0 1, y is chi square on m, degrees of freedom and they are independent. Let us look at x square. So, x square is z square divided by y by m, but z square, if z is normal 0 1, we know that then z square is chi square on 1. So, this can be written as chi square 1 on divided by 1. Y we know is chi square m divided by m, but y and z are independent. So, z square and y are independent. So, that means they are independent. So, this is a chi square 1 divided by 1 whole divided by chi square m divided by m. That means, this is nothing but f on 1 and m degrees of freedom. So, what it suggests is if x is t distribution on m degrees of freedom, then x square is f distribution on 1 and m degrees of freedom. So, there is some relationship between t and f also. Now, let us look at x. Suppose it has f on n1 and n2 degrees of freedom, then x has the same distribution as chi square n1 divided by n1, chi square n2 divided by n2, their ratio, and the two are independent. I look at 1 by x, which is same as ratio of chi square n2 by n2 divided by chi square n1 by n1. So, this is again ratio of 2 chi squares divided by their degrees of freedom, except that now the roles of n1 and n2 have changed. So, by the result which we did, this will have f on n2 and n1 degrees of freedom. So, what it suggests is if x has f distribution on n1 and n2 degrees of freedom, then 1 by x has f distribution on n2 and n1 degrees of freedom. Note that if x has Tm, then distribution of x is symmetric about 0 and its kurtosis is given to be this, which is greater than 3 for m greater than 4, because kurtosis would exist only for m greater than 4. Thus, a T distribution with m greater than 4 degrees of freedom is symmetric and leptokurtic, that it has sharper peak and longer flatter tails. So, what would happen is, so T distribution looks like this. Its PDF would increase from minus infinity to 0, then it would decrease. So, it is unimodal. It will have its peak which would be much sharper than the normal one, and so that means it will have a longer tails. Note that the kurtosis nu1 decreases as m increases. So, kurtosis would decrease as m would increase, and as m goes to infinity, you can say it goes to 3, which is same as the kurtosis of normal 0 1. So, this suggests that possibly this T distribution for large degrees of freedom is the same as the normal distribution, which is in fact true. As m goes to infinity, the T distribution with m degrees of freedom can be approximated by normal 0 1 distribution. Let us talk about quantiles of T distribution. So, suppose x has T on m degrees of freedom for a fixed alpha belonging to 0 1, let Tm alpha be 1 minus alpha's quantile of x. That means fx Tm alpha, which is probability x less than or equal to Tm alpha, is 1 minus alpha. Then, since the distribution of x is symmetric about 0, so fx minus Tm alpha would be same as 1 minus fx Tm alpha, because x has same distribution as minus x, which is same as alpha. So, that means if one has to get the alpha's quantile, it would be nothing but minus of 1 minus alpha's quantile. So, which is all right, because if you look at T, if this region is alpha over here, this region would also be alpha, minus Tm alpha, and this would be Tm alpha. Now, suppose that x has f on n1 and n2 degrees of freedom. For alpha belonging to 0 1, let f n1 and 2 alpha be the 1 minus alpha's quantile of x. That means fx n1 and 2 alpha is same as probability x less than or equal to f n1 and 2 alpha is same as 1 minus alpha. But I convert this probability into 1 by x. So, that would be same as, because probability x greater than 0 is positive, probability x greater than 0 is 1. So, I can convert this inequality in terms of 1 by x. So, probability 1 by x greater than or equal to f 1 upon f n1 and 2 alpha is same as 1 minus alpha. But 1 by x has the same distribution as f of n2 n1, we have just seen. So, this is equivalent to saying that probability 1 by x less than or equal to f of n1 and 2 alpha is same as 1 minus of 1 minus alpha, which is same as alpha. So, that means this quantity is nothing but alpha's quantile of f n2 n1. So, that means f n2 n1 alpha is same as 1 upon 1 upon f n1 n2, right. So, that is what you get, f n1 n2 alpha multiplied by f of n2 n1 and 1 minus alpha is 1. So, before I end, let me give these two take home problems. So, let Z1 and Z2 be IID normal 0 1. So, that Z1 by Z2 has same distribution as Z1 by modulus of Z2, hence so that Z is equal to Z1 by Z2 follows chi-square distribution, that means Z has T1. Let x1 and x2 be IID normal mu sigma square random variables, so that x1 plus x2 and x1 minus x2 are independent. Find the PDF of this. So, take these as your take home problems. This is all for this module. Thank you for your patience and have a great day.